My name's Marc Baldo. I run the Center for Excitonics here at MIT. We were recently awarded an energy-focused research center called the Center for Excitonics. It's a $20 million program from the Department of Energy over 5 years. It's being funded through the stimulus package. The call for proposals was design a center that's going to address some important problem in solar energy. And we chose to work particularly on this one topic of excitons because we felt it was actually the core to the scientific challenge. And plus MIT had a fantastic team here, and we're also working with Harvard and Brookhaven National Lab. So between the three institutions we felt we had a really good team and we had a really good opportunity to take a crack at an important problem both scientifically and technologically. The problem we're working on is something called an exciton. An exciton is a nanoscale packet of energy, and the purpose of our center is to control and direct those packets of energy. So for the first time, can we control energy on a nanoscale? And can we control where it goes and what we convert it into? Can we convert it into electrons? Can we convert it into light? I mean, most solar cells have to have some kind of crystallinity, and that just means inevitably it's slow making them and takes a lot of money because of that. So if we can break that reliance on highly structured, well-organized materials and move to an excitonic material where the energy is localized so it doesn't see defects around it so much. If we can move to that, it's compatible with spray coating, solution coating, float glass kind of manufacture. Those kinds of technologies could really have a big impact on our energy problems. So when you look at a picture of a city, you just see all this light coming out of it. And all of that just speaks to the massive amount of energy that we use on lighting. 30% of the US electricity generation goes to lighting. And so it also says if we can make that just a little bit more efficient, we can have a huge impact on the amount of energy that we need and how much it's going to cost us. The sun generates about 1 kilowatt of energy per square meter. So for every 10 square feet, there's about 1 kilowatt of energy. And so if you add that up and you spread that out across the whole country, it's a massive amount of energy, much more than we use today. So we can convert that, even at a fairly low efficiency, it gives us the possibility for a ubiquitous source of energy. In theory, we wouldn't actually need anything else other than solar electricity to meet all our energy needs if we could harness the power of the sun cheaply enough. If you look at the example of photosynthesis, which is a good example of a widespread system of solar energy conversion, it's completely based on excitons. And there's in fact circuits for excitons in photosynthesis. In conventional engineering, we're a long way behind being able to build things like circuits for excitons. But our center's designed to try and take us towards that level of technology. We're not going to build any new buildings, so the labs are already set up. Basically, this center is going to tie together a bunch of work into a coherent effort on looking at this important challenge. And it's also going to make sure that the scientific interactions between all the different pieces of the problem are very strong. Within MIT, we have theorists working on aspects of how excitons move around. We have physical chemists building new machines to image and take data on excitons. And we have engineers like me that are going to try and build devices that build off the scientific efforts in the center. We've got very well-defined problems that aren't easy to solve, and it's going to take a lot of chipping away from a lot of very talented people to address these. The center gives a focus to these problems. I mean, there's a lot of things we could work on in the world, but we decided as a group that this particular coherent arrangement of tasks from science through to technology is a very practical solution to the big picture challenges that we face. I think this is a once-in-a-lifetime opportunity to work on a problem of this scope. We've been given a fairly liberal rein to go work on what we think are the most important problems and then report back to DOE and said, like, this is what we think is the problem and this is what we've done about it. And so we think that's kind of a unique opportunity because it's not too top-down managed. It's going to allow the free flow of ideas to come out of the center. And plus the sheer scope of it, the ability to, for the first time, have a center that combines theory all the way through to devices is sort of unique in my experience.